Hello everyone, so we're going to be looking at chemical formula today. We've left behind atoms and bonding, we've finished that now, and you're going to need the following. You're going to need your data book, which I'll ask you at some point to annotate, and also a pen and a paper to practice the formula. We've also got an associated Google form to go with this, so you can get that to us as soon as possible. The chemical formula is really, really important. It's one of the real foundations, the real pillars of chemistry and our understanding of chemistry. And we're going to be using the skills that we learn today in future lessons again and again and again. So it's really, really important that you get to good grips with this. As usual, if you have any questions, please get in touch with your teacher and we will get back to you as soon as possible. So let's get started with our prior knowledge questions to get your brains in gear. So here we go, first one. The shape of a molecule of nitrogen hydride, NH3, is likely to be, off you go. So with NH3, we have 4 atoms in total. So the only possible shape that could form in this case would be trigonal pyramidal. Now, just a word of warning here, I changed the question slightly from how it is in the exam, and I've added the formula in. In the question, you weren't given the formula NH3. You had to work that out for yourself. So that's one of the skills that we're going to be learning today, how to work out chemical formula to help you answer questions similar to this here. Next question. So similar to what we've just been looking at, chemical bonding and the properties of chemicals, this one here is asking, show the properties, which one of those there, A, B, C, or D, shows the properties of a covalent network compound. So if you want to pause the video and then have a go at this, please. So I would jump straight to the conductivity, really. We should hopefully remember that covalent chemicals, that they do not conduct electricity at all, whether that's a solid or a liquid. The reason for this is that because they don't have any freely moving ions or freely moving electrons. So they don't have any freely moving charged particles. There is an exception if you remember that graphite is the exception to this, but generally covalent networks do not conduct. So we have an example here of a covalent network, and in this case, this is silicon dioxide, which has the formula SiO2. So we've identified it's either A or D. So the difference now between A and D is in their melting and boiling points. And we're hopefully going to be able to identify that in a covalent network, you have to break lots and lots of very strong covalent bonds. Therefore, it's going to have a high melting point. A covalent molecule, you only break the weak intermolecular forces, therefore they have a low melting and boiling point. So in this case, our answer is D. We have lots of strong covalent bonds that need to be broken, and we do not have any freely moving charged particles. Next question. So this is a little bit of revision from S2. You have to name the elements present in the following compounds. Here's a little bit of a clue to help you out. With the endings, our endings give us is like a code. It gives us a helpful clue to help us name these elements. So if we have the ending IDE, that means that we have 2 elements present. If we have the ending ATE, we have 3, and one of them is definitely oxygen. So use that to help you answer these 4 questions. And when you're ready, unpause the video and we'll go through the answers. So calcium oxide, we have calcium and oxygen. The IDE bit, as it says below, indicates that we only have 2 elements. For nitrogen hydride, again, we only have 2 elements. We have nitrogen and hydrogen. And now for copper carbonate, we've got the ending ATE, so we therefore have copper and carbon and oxygen as well. For magnesium sulfate, we have magnesium, sulfur, and oxygen. And this skill, this ability to identify the elements that are present in compounds just from their name, is going to help you out enormously in the coming lesson. So on to today's lesson, and what we're going to cover today are 2 things. We're going to look at 1, can you understand exactly what is meant by chemical formula? And then also, can you write the formula of elements and also of covalent chemicals? And we'll do ionic chemicals at a later date. So our definition for chemical formula is as follows. It is the number and type of atoms or the proportion of atoms in a chemical. So the number and type of atoms is a little bit easier to understand. So if I had a glass of water, for example, and if I was to zoom in on the atomic scale, millions and millions of times, I'd see that I have trillions and trillions and trillions of these water molecules. And each water molecule can be drawn in this way. We've seen this dot and cross diagram. So those individual water molecules, well, we have 2 hydrogens and we have 1 oxygen. So that tells me in that particular molecule, that's all I have. So it gives me a chemical formula. It tells me the number and it also tells me the type of atoms. And we know, or hopefully we should know, that the formula of water is H2O. What we want to know though is what exactly does that mean, and also how can we work this out? How could we work out just from the name of a chemical that we have 2 hydrogens or 1 oxygen, for example? It is really important to know how to write these chemical formulas though. So one of these is correct and 3 of them are wrong. And the one that is correct is this one here. And the reason why it's correct is how it is written. So first off, if we have a number in a chemical formula, we can imagine we have sort of a line that goes through half of that molecule, as I've drawn there in orange. Well, our number has to go below that halfway point. We call that subscript. Also, what's different about all of these here is that we have the H and the O are the same, well, they're in capitals. And the reason why they're in capitals is because that's what their symbol is on the periodic table. That's the element symbol. So hydrogen symbol is capital H, oxygen symbol is capital O. Therefore, we use those in our formula. So the numbers are subscript and the letters are the same as their symbol. So that's really, really important. So we're going to look at the elements formula, or formula of elements rather, first, because they're fairly straightforward to do. Thankfully for us, most of the formula of elements is just simply their symbol. So lithium's formula is Li, copper's formula is Cu, and so on and so on and so on. Now what that means, or what that doesn't mean rather, is that in lithium we have 1 atom of lithium, or in copper we have 1 atom of copper. That's not the case. If we were to look at a sample of lithium, for example, it may look something similar to this here, where the green spheres are the positive lithium ions and the black spheres are the delocalized, the freely moving electrons. The reason why lithium's formula is Li as opposed to Li, however many atoms there are there, Li 2 trillion or whatever it is because each of those atoms is exactly the same. So therefore we just use the symbol Li. In the same with copper, if you get a sample of copper, every single atom is the same, therefore we just use the symbol copper. There are, however, 7 elements for which this doesn't apply to, and these 7 elements are known as the diatomic elements. Diatomic meaning 2 atoms. So the diagram I've got there is a picture of hydrogen. It's a gas canister filled with hydrogen, and if you were to look inside that and you could see the individual hydrogen atoms, you notice that they were paired up together. And these elements which are paired up together, there are 7 of them, and as it says there, we refer to them as the diatomic elements. Thankfully, there are only 7 of them, but we do need to commit them to memory. So if I was to ask you in a few lessons' time, what is the formula of oxygen, what is the formula of chlorine, what is the formula of nitrogen, hopefully you wouldn't say O or Cl or N, you'd say O2, Cl2 and N2. And all of these are paired up together in the same way that the hydrogen was there as well. Now there's 2 ways that we traditionally teach how to remember the diatomic elements. We use a mnemonic for the first one, where the letter of each of these corresponds to a letter of the diatomic elements. So have no fear of ice cold beer, rhymes as well, which is quite helpful. And then we've also got this here, Mr. Brinkelhoff, whereby the Brinkelhoff part represents the elements in our diatomic elements. So that's the formula of elements. What we're going to look at now is the formula of covalent chemicals. So hopefully you can remember we have 2 types of covalent chemicals. We have covalent molecules and we also have covalent networks. And in a covalent molecule, our formula states the number and the type of atoms in each molecule. So the example here I have is a picture of water, and each of those water molecules has the formula of H2O because we have 1 oxygen and 2 hydrogens. For covalent networks, we have the example here of silicon dioxide. So the formula of silicon dioxide is SiO2. Now that doesn't mean that we have one silicon and two oxygens. It means that in that compound, in that network, the ratio of silicons to oxygens is one silicon to two oxygens. So covalent networks, the formula states the ratio of atoms in the substance. So that's the formula of elements, and we're now going to move on to the formula of covalent chemicals. And there are two methods for working out the formula of covalent chemicals, depending on what their names are. So, for example, here we have carbon monoxide and we've got nitrogen dioxide. And the bit in front of the oxygen there, the mon and the di, well, that tells us that we have to use a set of rules for working out the name here. And we're going to go through the set of rules there. We refer to the mon and the di as what's known as being prefixes. So we have 6 prefixes here: mono, di, tri, tetra, penta, hexa. And you're probably familiar with penta as in a pentagon, or hexa as in a hexagon, or tri as in a triangle. Well, these words or these prefixes indicate to us a number. So mono equals 1, di equals 2, tri equals 3, and so on and so on. So what that tells us now is how many of these atoms there are in a particular chemical. So in the example of carbon monoxide, well, there's nothing in front of the carbon, there's no prefix there. Well, if there's no prefix, then that tells us we've just got one of that chemical. So therefore we have one carbon in a molecule of carbon monoxide. The monoxide bit, well, the oxide refers to oxygen. The mon, if we were to look at that table there, means 1, therefore we have 1 oxygen. So carbon monoxide literally reads as 1 carbon, 1 oxygen, and that's our chemical formula. For nitrogen dioxide, we have 1 nitrogen because there's nothing in front of it, there's no prefix, so therefore there's just one of them. And then the dioxide, well, that equals 2 oxygens, therefore it is 1 nitrogen, 2 oxygens, NO2. So if you guys want to have a go at these, please. We've got manganese dioxide, we've got phosphorus pentachloride, and then we've got dihydrogen monoxide. So hopefully we found for manganese dioxide, it's not commonly used in chemistry classes, manganese. So hopefully you found that. It's a transition metal, it's Mn, and then the dioxide is 2 oxygens, so it's MnO2. Phosphorus pentachloride, it is PCl5, 5 coming from the penta part, and then dihydrogen monoxide is the more commonly or less commonly used name for water, the scientific name for water, dihydrogen, 2 hydrogens, monoxide, 1 oxygen, H2O. So we have to use a different method for working out the formula of covalent chemicals if those covalent chemicals in their name, they don't have a prefix. So a lot of covalent chemicals, in fact most of them, don't have these prefixes. So the way that we work out the formula is by something called the valency. And the valency is the number of bonds that a particular atom can form. So if you look at a data book, you won't see the valencies written in, but what I ask my pupils to do normally is to annotate their data book. In other words, to add the valencies to a periodic table in their data book. So now would be a good point to do that. So if you want to pause and then get your data book out and then write in the valencies, and the valencies go above the group numbers. So you may notice that the valencies are similar to the group numbers. So group number 1, the valency is 1. Group 2, the valency is 2. Group 3, the valency is 3, which means it wants to form 3 bonds. Group 4 is 4, and then it goes backwards, so it differs from the group numbers. So group 5, we have a valency of 3, then 2, then 1, and then 0. And let's have a think about these here. So let's take the example of nitrogen, for example. Nitrogen is in group number 5, which means it has 5 electrons in its outer shell, which means it wants to form 3 covalent bonds. So nitrogen wants to form these 3 bonds, therefore it has a valency of 3. If we take chlorine, which has the atomic number of 17, that's in group 7, which is one of the halogens. If it's in group 7, it has 7 outer electrons, therefore it wants to form 1 covalent bond, therefore it has a valency of 1. And then the noble gases, well, they don't have a valency because they don't want to form any bonds. They've all got filled outer electron shells, and therefore their valency is 0. So we're going to look now at how to use these valencies to work out our formula of covalent molecules. So the way that we do this is by something called the crossing over method. So I've got a chemical here. What is the formula of nitrogen chloride? There's no prefixes here, so I can't use them. So I have to use this crossing over method. So the way that I do this, and the way that I recommend that you guys do this too, is as follows. First off, you write the symbol of your chemical, so N and then Cl. Above that, you write the valency. So you go to your data book and you see that nitrogen has a valency of 3, chlorine has a valency of 1, and you write it above them. You would then rewrite the symbol below, and then you would take the valencies and cross them over, like so. So the 3 above the nitrogen has now been taken and it's been crossed over, and that now goes below the chlorine. So it goes subscript for the chlorine. The chlorine's valency of 1 has now been crossed over, and that goes to the nitrogen. And what this now gives us is a chemical formula. It gives us the chemical formula of 1 nitrogen and 3 chlorine, so NCl3. This now is in the simplest ratio. We cannot simplify a 1:3 ratio any further, therefore we just leave it as NCl3. And you may be asking, or you may be thinking, where's the 1 gone? Where's that valency gone? Well, the symbol N represents 1 already. So our formula is NCl3 as opposed to N1Cl3. Let's have a go at another one. So here, what is the formula of hydrogen sulfide? Well, again, I've taken the symbols, I've written the valency above them, and now I'm going to write the symbols again below, and I'm going to cross over those valencies. And in doing so, that gives me a formula of H2S. Is that the simplest ratio? Well, yes, it is. A 2:1 ratio is the simplest form, so we cannot therefore simplify it any further. So our chemical formula for hydrogen sulfide is H2S. Why don't you guys have a go at this one on your own? So pause the video and then see if what you come up with. So we've got our silicon here has a valency of 4, our oxygen has a valency of 2. We're going to cross over those valencies. We've got Si2O4, so our formula is Si2O4. Except we haven't yet finished because it isn't the simplest ratio. A 2:4 ratio is not as simple as it could be. If we simplify it, it becomes SiO2 with a 1:2 ratio. Okay, so we've got the opportunity to do some more practice now. So if you want to pause the video, have a go at all of these, take your time on them, do the full workings as you're starting to learn them. And then when you're ready, you can check the answers by unpausing the video. So let's have a look at the answers here. So those are the answers. So if you can mark these yourself, that would be great. If you're getting these incorrect, the usual thing to do is to get in touch with your teacher, and maybe we could, or you could come to the Google Meet and we could go through how you can do these. And once you've done that, once you're happy with this, can you then go on to do the associated worksheet? And again, if you have any questions, get in touch. And thank you for getting this far. Bye for now.